Thank you so much, Professor, for agreeing to do this interview. Would you introduce yourself and tell us more about your educational background? Where did you go to school?
All right. So first of all, thank you for inviting me to talk to you. I think what you're doing is important for people to understand the scientific process, among other things. So my name is Michel Barsoum, and I am half Egyptian, half Swiss. I got my bachelor's degree in material engineering from the American University in Cairo. And then from there, I went to University of Missouri, Rolla, where I got a master's degree in ceramics.
Mhm.
And then I went from there to MIT, where I got my PhD in ceramics in 1985.
Yeah.
So long time ago. And I came straight from there to Drexel University, and I've been at Drexel now 40 years. Um, yeah, in the Department of Material Science and Engineering.
Yeah. So, during your school, I mean, before you go to university, would you talk about it? How did it go? I mean, in the school, did you have labs, experiments? How you become familiar with material science? Initial before you get into the university degree.
Yeah, so that's an interesting question, and I call material science and engineering, the accidental profession
Mhm.
because very few people know what it is, and so they jump in. So I at the beginning of the summer before I went to university, I wasn't sure what I wanted to do, and I was my father was a dentist, so I sort of thought maybe. So I met this friend of mine at the beginning of the summer. At the end of the summer, became a dentist, and he's now working in Long Island. And I went to the American University, become a material science and engineer. So it's one of those things where, like I said, accidental profession.
I see. So when you went to university, you mean one of your friends suggested, and you chose.
Well, the American University in Cairo,
Oh yeah.
that was the draw. That's a private university.
Mhm.
They also gave me a full ride, so that was nice. And yeah, it's still uh, AUC is still going strong.
Yeah. Which subjects did you like more when you started doing your
Yeah,
degree?
it's an interesting question. I mean, I was very good, and usually you like what you're good at. So I was good in math and calculus and chemistry. I didn't really like chemistry, no, but
Mm.
in physics and especially solid state physics, and most of my material science and engineering courses, metallurgy, ceramics, polymers. So that all spoke to me. As soon as I got there, I realized what materials science and engineering was. It was like I found my calling, really.
And I guess nowadays it's the material science and engineering. It has different branches: ceramic, metallurgy. Was it the case at the time, or it was just material science and engineering, and you learn everything, metallurgy, ceramics, or you could choose specifically you want to work on, or you want to take ceramics courses?
Yeah, no, I think the history of the field is the opposite of what you just described. In the past, I mean, metallurgy was sort of the first, I guess, material material kind to make it into research because
Mhm.
of the war and arms, etc. So and nuclear power. There's a very strong federal support to do that, and that's global. So and they sort of were in parallel. So you had people doing polymers, people doing metals, and doing people doing ceramics. And if you go back 30 years, you will find a lot of metallurgical departments and ceramic departments
Mm.
in the same university or in different universities. And then the modern idea then became, well, why we really should sort of put them under the umbrella of material science and engineering. And that came later. When I came here in 77 to the
Hmm.
States, there were a lot of ceramic departments, just ceramics, and a lot of metallurgical departments, just metallurgical. Now, if you go and look, I think the number of ceramic departments has dropped to two. And I don't know how many metallurgical departments there are, but they're a lot less than they used to be. And they're all under the umbrella of material science now.
Okay, yeah, okay. When I did it, I don't belong to that time. I mean, I belong to modern material science and engineering era. When did I do that? 2006. 2006. Yeah, in Iran, we have different branches. You can choose which one you want to go
Yeah,
for.
right,
Uh,
right.
and please walk us through your graduate program in during your master.
Yeah,
Um,
so in my
what did you do?
master's, I was working on the wetting of silicon on silicon carbide. So I was looking at that. And what I did is I measured the contact angle between molten silicon and different silicon carbides. And from that, we were trying to understand how they would interact together.
Mhm.
So that was pure, if you will, yeah, that was ceramics in the sense that we were using silicon carbide. And then from when I went to MIT, I changed completely and I was working on glass solid electrolytes for lithium.
Mhm.
We were making different glasses. So I was processing different glasses and then putting them in cells, in lithium ion cells, and measuring their conductivity and how the lithium went through the glass, et cetera, et cetera.
Okay, interesting.
Yeah.
And did you do a postdoc?
No, I went straight from MIT to Drexel.
Okay, amazing. Uh, so let's talk about max phase. Is it called max phase or call it MAX? I guess it's a max phase, right?
Yeah, Max Phase, yeah. Mhm.
Yeah. So before I ask you about your contribution to this class of material, would you just briefly gives us a introduction to the history of this phase and why is it important?
All right. By the way, after we hang up, I'm going to send you a link to a presentation
Hmm.
that I just recorded for I was supposed to give a sort of historical perspective on the Max phases and the future just last Thursday. But
Okay.
then my flight got canceled, so they asked me to record it. So I'm going to record it, and it's yours. You can, and in there I summarize the history.
Mm.
So I can do that now. And essentially, Hans Nowotny was a solid state chemist, and in the 60s, he discovered an incredible amount of new phases, carbides, nitrides, borides. It was unbelievable. I don't know, they discovered, 100, 200, 300 completely new phases that people had not heard of. And then, but they were solid state chemists, so they made a small amount of the material
Hmm.
and characterized it by XRD and said, okay, we have the material, here's the XRD, and thank you very much. And that was it. So the papers were short, two or
Yeah.
three pages. Anyway, so then they lay dormant in the literature essentially till 1996 when we made the big discovery on titanium silicon carbide. And the max phases are really M sub n plus 1 A X N. All
Mm-hmm.
right, so if n is 1, we get what we call 2-1-1 phases. And the 2-1-1, the M is an early transition metal.
Mm-hmm.
The A is an A group element, and the X is carbon and or nitrogen. Okay.
Yeah.
And so we made them, we were the first really to make them single phase and fully dense. So we were the first to start characterizing them. And what we discovered blew our mind. So I'll give you the two, well, the highlights of max phases are as follows.
Mm-hmm.
Some of them are more conductive than titanium metal. Some of them are more thermally conductive than titanium metal. Some of them do not, they don't thermal shock, so we can throw them in from 1350 degrees C in water. Nothing happens to them. But I think their one neat or unique characteristics is machinability. So we make them at max phases, and in my lab for many years, we make a max phase, and then to test if it's a max phase or not, we try to cut it with a manual hacksaw, right?
Mm-hmm.
Manual hacksaw, and if it cuts, then we know we have a max phase. If it doesn't, we go back and start playing around with our processing condition. And so when I found that, I wrote a paper uh, that I submitted to Nature and Science, who declined it. I finally got it published in Journal of American Ceramic Society, and the title is TI3SiC2, a
Mm-hmm.
remarkable ceramic. Okay, and so the word remarkable is in the title because it was so mind-blowing.
Mm-hmm.
So that was the first one, and then we very quickly realized, once we made one, that Nowotny discovered 50 of them. So for about a decade, my graduate students and I, we would just go in and pick one or two or three and just make them
Mm-hmm.
for the first time ever, characterize and find their properties. So it was a very exciting time. I told my students it's like discovering, 15 new pet planets because we never knew what we were going to get.
Mm-hmm.
And that's part of the thrill for me about this job. So that's the sort of that's the history, and then Nowotny and coworkers had discovered the n=1 and n=2 phases. So it was 2-1-1 or 3-1-2. And in 1999, we discovered the 4-1-3 phase. That was the first indication that there is another family.
Mm-hmm.
And the only difference between the three is how many transition metal carbide layers you have. So in 2-1-1, you have 2 layers. 3-1-2, you have 3 layers. In 4-1-3, you have 4 layers. But the key to all the properties is then after you get these slabs of carbide, then you have a layer of pure A. And A
Mm-hmm.
is, there's about, again, in Nowotny's case, there's about maybe 10 or 12 A group elements. And they're pure. So you have layers of pure aluminum or layers of pure silicon or layers of pure lead or tin, et cetera, et cetera. And that pure layer then is what gave them their unique properties, including machinability and thermal shock and conductivity, et cetera.
Yeah, that's interesting because we know ceramics as brittle materials. We can do I don't know, all these things on them to, they don't have good mechanical properties. And
Well, they're not plastic. I mean, they're not
yeah,
ductile, yes.
yeah. So interesting. So initially, I would like to know why did you become interested in these types of materials?
That And so what we did is we took titanium and boron carbide, and we reacted them, and the process worked beautifully. We got titanium diboride, titanium carbide composites that were very hard, and I actually patented the process
Hmm.
because there was a little trick in it. Anyway, and then it was funded by NSF, and then the funding was coming to an end, and so I was looking for something else. So the one problem with titanium diboride, titanium carbide is that they're not oxidation resistant. So to get oxidation resistance, usually you need silicon is one of the elements that forms a nice layer, protective layer,
Hmm.
and renders your material oxidation resistant. So I told my graduate students, said, okay, why don't you take titanium, react it with silicon carbide, and what we will get is titanium disilicide and titanium carbide composites. So he said, okay. And then he comes back the next day. He says, there's this ternary compound, titanium 3SiC2. What should we do about it? I said, well, try to make it. So he said, okay. So he made it. And then I said, all right, let's start doing some characterizations. So the first thing I said, the easiest thing to do is just throw it in water and see what happens. So he said, what temperature should I start? I said, 600. So he does that, comes back the next day. He says, nothing happened. I said, what do you mean nothing? I said, nothing happened. I said, well, try 1,000. He tried 1,000, came back and said, nothing happened. I said, that's unheard of. So I said, try 1,400. So he tries 1,400. And again, nothing happened. Actually, it got a little stronger. So that's when we realized, okay, this is not your irregular ceramics. So we started measuring other properties like conductivity. And like I told you, they're very conductive with electricity and heat. Machinability. That's when we discovered the machinability. And I'll never forget that day. We made a sample in the hot press, and I went down to the machinist, who was a buddy of mine. I said, Mark, please drill this. So he looks at me, he knows I work in ceramics, says, okay. So he puts a drill and he pushes it on the sample, and he gets this horrible sound, not machinable. So he goes back and he sharpens the bit, comes back, does it again. He gets this again horrible noise. And then he went back. I don't know why he went third time, but he sharpened it again, came back. And then I still get goosebumps. So the thing basically made a little bit of really ugly noise, and then all of a sudden it went shoo, more like all of a sudden you went into a piece of wood.
Mm.
And I looked at my student, I looked at Mark, and I go, oh, that now we really have something remarkable. Yeah, it was yeah, because my original idea, we are going to make titanium silicide, titanium carbide, like the borides. That's going to be a very hard material, et cetera, et cetera. Anyway, so that I think you can chalk to pure luck, I think. Um,
Yeah.
I mean, it's not 100% pure luck because we use this technique that I developed in hot pressing to make it. Other people try to make it and were not able to. So I'm not going to say it's 100% luck, but there's a good element to it.
Yeah, you are very humble that you say it's like you have put time and effort on it to develop this material. Definitely, there are science behind it. Um, and later on, MXene was born, right? Is that true?
MXenes. Yeah,
I'm pronouncing it wrong. MXene?
MXenes. Yeah.
MXenes.
So
Okay,
you
yeah.
pronounce the A, but it's not there.
Yeah, MXenes.
MXenes. Yeah,
Uh,
MXenes. Yeah, MXenes are now. I don't know if you looked at the number. They're just beyond anything I've ever seen.
yeah.
Yeah, so how do we discover MXene? So my colleague Yuri Gugotsi came to my office one day and he said, the max phases are conductive. I said, yes. He said, they're oxidation resistant. I said, yes. And he said, well, and they're layered. I said, yes. He says, why don't we propose to use them as anodes in lithium batteries? So I said, okay, that was my PhD. So I said, all right, why not? So we wrote $1 million proposal to DOE and it got funded.
Hmm.
And then I hired, because so the guy who discovered max phases with me, Tamara Rockhe, was from Department of Material Science and Engineering in Cairo University.
Hmm.
And to get hold of him, I called my father, who was also a professor in Cairo University, and I asked him to go to that department and get me Tamer's coordinates because I didn't have them. Anyway, so he did, and Tamer came here, and then the rest is history. So this time, as luck would have it, I had another Egyptian, Michael Naguib, and he wanted to do a PhD. So I said, "Great, I got a very nice project for you. Here you go." So for about 6 months, we tried to get the lithium to go into the max phase, and it was not working. It was not working, it was not working, it was not working. And so we thought, all right, what if we try and etch out some of the elements in this material? So one day Mike comes, he asked me, can he use HF? And I said, sure, but be careful. And but he also had asked Yuri before, and Yuri said, no, it's too dangerous. Okay, so but anyway, so he went ahead and did the experiment, and he came back with a very interesting X-ray, and that's when we discovered that yes, if you put this material in HF, the max phase in HF, you go and you etch out, selectively etch out the A layers, and you immediately go from 3D to 2D. And so that's where the name came from. So the A, we got rid of the A and we put the MX together. And then we added E and E to make the connection to graphene, which was
Hmm.
another conducting material, 2D conducting material. So that's and there's a very big element of luck there. I don't know if we have the time to go through it, but
Yeah, why not?
all right. So we Drexel had licensed the max phase technology to a company called Kanthal. They
Hmm.
make heating elements in Sweden. And so Kanthal came and started making max powders. So we had some so they decided to make two composition, titanium 2 aluminum carbide and titanium 3 SiC2. Okay.
Hmm.
So we had some titanium 2 aluminum carbide. Michael took it in the lab, put HF on it, washed it, and X-rayed it. And what we got was not 211, but 312. So we were extremely puzzled at the time. Why would you etch 211 and get 312? Anyway, a week later, we realized that the material that Canthal is making was not pure 211, actually had like 15, 20% 312. And it was that 312 that survived the acid. The way I recount the story is, had Canthal been truly making 211, what they sold, we would never have discovered MXenes, because under those conditions that Michael used, 211 dissolves completely.
These types of materials, they got enormous amount of attention, I would say. Uh,
Enormous, yes. That's the
uh,
word.
I don't know how I should put it.
Yeah, no, I run out of adjectives.
So, why is that? I mean,
Well,
is
there
there
are many
any?
reasons for it. Okay, I think there are many reasons. The one that there are few, the one that I think is probably the most important was the process itself was relatively straightforward. You just
Mhm.
put it in acid weight, take it out, wash it, and you have 2D material. Whereas other 2D materials, you needed to, I don't know, first delaminate them, and there was a multi-step process. This was basically a very simple
Mhm.
process. And then the properties that you got were extraordinary because MXenes are the first two-dimensional metals that are out there. There have always been two-dimensional insulators, there's always been two-dimensional semiconductors, but never two-dimensional metals. So that's another factor. Then the third factor is the when my student Michael Guido, when he came and worked with me, he replaced the HF by lithium fluoride and HCl, much safer chemicals that form HF in situ. So the process is the same, but
Mhm.
you didn't have to deal with HF. So that again made it easy to make in large quantities and relatively now safe because didn't need to use HF. And then the properties you got were just what you see.
Yeah. And you have managed to publish hundreds of articles, several, I don't know, if you, not maybe not hundred, but if you tens of patents. Uh, how did you manage to do all this work? It takes a lot of time. Um, it would be nice if you can tell us more
Yeah,
about.
no, I have a very good answer to that one because I know exactly how that works. And then this answer also will answer some of your uh, questions, other questions. So the first thing is when you like something, when your work is your passion,
Hmm.
then it's not work. Okay, it's not work. You're having fun. And that's what, I mean, yes, I published a lot of papers and yes, I worked hard, but it was to this day, many days I wake up and I don't want to do anything but finish a paper or finish a proposal because it's so much fun.
Yeah.
So, and again, that is a big element of luck here because I lucked into materials and it turns out to be my calling. And, so if you ever find your calling, then I would tell anybody listening, if you find you, whatever it is, you find your calling, just go with it. Um, so yeah, that's one. Yeah, I think that's the best answer I have is, yeah, if you work, it's amazing what you can accomplish if you focus for 8 hours in a row.
Yeah.
Okay, so yeah, I do that. I can focus for 8 hours in a row. And of course, I have the help of my students, and they it's an iterative process. They write a draft, I mark it, send it back a few times, and then it's good enough to submit. Yeah, so
Yeah. And
the other factor I think that I should really that is important, I should mention, is the fact that whenever you're working on a new material,
mhm,
you sneeze and you get a paper. You're the first person to do something or to discover something. So whatever you say about that something, because it was not discovered before,
mhm,
is interesting to editors and reviewers. And so, you don't have to spend much time. So the way I describe it is it's low hanging fruit. So the work I do when we discovered the max phases, we discovered MXenes, and now when we discovered those one-dimensional lepidocrocite, first we go for the low-hanging fruit.
mhm.
These are basically simple experiments, give you very good information, and they're not profound, but they're the first of their kind. And then whenever we start something and it turns out that, yeah, we may be onto something, but it's going to take a while to prove it, then I say, all right, we have more important things to do, and we move to something that's more low hanging. So that's one thing. I think the other factor that sort of expanded when we discovered MXene, well, yeah, is I started building a global network of friends and colleagues.
Mhm.
And that's very important because now you're multiplying your efforts by, the number of people you're working with. So that having a large network and working with good people who are interested in what you're doing, if you can convince them to work on your material, quote unquote, then that's another way to, increase the number of publications that you can get.
Yeah. So the number of the publications is something, and publishing high quality articles, that's another thing. Most of your work, they are highly cited. So how is it possible to manage to uh, to keep the quality high? That's also another thing I would love to know.
Mhm.
Because you've been considered recognized as the highly cited material researchers in multiple years.
Mhm. The
2009.
last four, no, the ones you have are not right. I think the last 3 or 4 years, yes, I was the highest with this, what they call a C index,
Hmm.
which is a combination of H index and number of citations. Yes. Um, so to answer that question again, ha, okay. I think so. Very early in my career, I decided that I loved doing science and I hated managing science. What does that mean? It means that I like writing papers, proposals, not so much. I like to do the science, but not. But so when you start your career as a young faculty, um, you sort of have to make a decision. You don't have to make a decision right away, but 4 or 5 years into your career, you have to make a decision. So if you have a big group, 15, 20, 30 people with postdocs and the big groups, right? The empire builders, you really all you do is manage research in the sense that you continually have to go out there and get more and more and more and more funding.
Hmm.
And since you only have, 24 hours a day, then what happens is your research and quality takes a hit because really what you're getting is the as good as the postdoc you hired, that's what you're going to get. Because at the end of the day, you don't have time. You have to rely on your postdocs. Some are good, some are not so good. So what I did is I've always kept my group small.
Hmm.
Five, maybe 10, 5 to 10.
Hmm.
And so I would raise the money that I needed to keep these guys going, and then I would start writing proposals for
Hmm.
a year or two. Um, yeah, so that's one. Now, the benefit you get there that also answers another question that you have later is that I like to think of research like a small business. If you have a small business and you leave it to your employees to run, it's okay.
Hmm.
But if you're now there every day, then you know, then your small business will thrive. So that's what I am. I'm here every day. I'm with the students. You know, every every week they will get at least 2 emails from me. What's new? That's it.
Hmm.
In the title, what's new? All right. So that's important. And because sometimes, well, not sometimes, I mean, after you do research for 30, 40 years, your depth of knowledge is quite substantial. And so something that may escape your graduate students, um, what's the word, may escape their notice,
Hmm.
could really be something very important. And I have a few examples of those. And what I tell my students, and I say non-facetiously, is the way you do science is you make a hypothesis and you go test it. Okay? And most of the time, if you know what you're doing and you're a good scientist, you will get, confirmation that your initial hypothesis was good. But every now and then, you get this one result that doesn't make sense. And I tell my students, that's the one where I really perk up. Oh, really? So our hypothesis was wrong.
Hmm.
So now let's see what we got and why. So that's a second, very, very, so you have to be there. You have to be there almost on, I mean, I meet with my students weekly, every week of the year, more or less. I don't do too many conferences. Well, I used to, but not as much anymore. So yeah, so I'm there. And I think that that is one of the keys to a successful academic career. When I get a new graduate student, I bring them to my office, we chat, and then for I explain to them that they're going to have to work on at least two projects, preferably three, completely different. The mechanical properties of thin films, max phases and MXenes. Okay, and why is that? Okay, the reason for that is very simple. Have you heard of Murphy's Law?
Yeah, yeah, Murphy's Law.
Murphy's Law, right. So I figured out a way not to beat Murphy exactly, but to make him less devastating. So when you work on one project, and this happened to me when I was at MIT, you work on one project and a piece of equipment goes down that you need. Well, what are you going to do? You're going to sit
Mm,
there and twiddle your thumbs. And I'm sure you're in grad school, you had the same sitch,
exactly.
right? So the only way around that is to work with three different projects. Why? So one stops because of equipment or whatever. You didn't get the chemical. Then you
Mm,
switch to the second, you switch to the third. And I've had a few, and that's how we made some very large discoveries because of no pressure. You just go, you pick a good idea and you run with it. And then, I've had multiple students who started on one area and 2 years into their PhD, they actually switched to a much more exciting area,
mm,
and they still finished in well. By the way, the average for my PhD graduation is about 4 years. Some have graduated under 3,
great.
because once I realize it's that a student is not going to be learning anything new anymore, then I say, okay, you're good.
Mm,
So I've had that. Um, but I'm sort of all over the place. So the point is, and so the other advantage that this gives you when you are giving students like more than one project is you find what they like. You sort of you sort of they're doing all these things, but they really like doing this working in that particular area. And then that becomes, again, going back to the idea that if you're enjoying yourself, it's not work. And that's what happens. So my students, for the most part, are quite happy. They're extremely productive. And yeah.
amazing. These are good points for those who are in their early career as a faculty member. Uh,
Mhm.
so uh, you have received many awards, and if I just wanna read them, it takes half an hour. So when you started your career as a faculty, did you see yourself to
No, I
receive?
can answer that question. You don't have to explain to me. I mean, if you told me 40 years ago that I'm going to, meet two presidents and shake hands with the king and have an age index of 150, I would have laughed so hard. It's not funny. I mean, it's just like, it was not, yeah. And it's nice to get awards, but I would not trade them for my job
Mhm.
because it's because I mean, to this day, Mushtaba, I drive to Drexel sometimes and I am amazed they actually pay me to do this job. That's how I still feel 40 years later. So I'm really passionate about what
Yeah,
I'm doing, obviously. And again, once you find your calling, you are good to go.
yeah, that's a great point. So are you retired? I think you are. I mean, you are a distinguished professor. I mean, do you still are you still involved in research actively?
I'm not retired at all.
Oh, okay. Okay.
Not even close. I am still teaching graduate class in ceramics
Amazing.
once a year. And so yeah, so I'm not retired at all. I'm full time and I just turned 71 and I don't know what I would do with myself if I stopped. Is another sort of interesting conundrum. I can finish writing other books, which is probably what I'm going to do if I retire. But so long as I can attract funding,
Mm,
because you need funding to do research. So long as I can attract funding, then I'm going to stick around. At least maybe, you know, minimum 2 years more. So,
mm.
but 75 may not be a bad time to quit. But again, there's a lot of, we'll see what happens.
When I checked your webpage, I read this statement, our philosophy, what everybody needs to be doing on a windy day with a picture of you sailing. What does it mean?
That's another, I think, key to my success. And that is I work hard and play hard.
Mm-hmm.
And this is something that America has not figured out yet. But there are really, being half Swiss, I went to Switzerland many times and, and lived there over the summers and, observed and all that. And, there are two philosophies in this world. There is one that says you want to live to work. That's the American system. And
Mm-hmm.
European system is work to live. What does that mean? It means that so when a student comes and tells me, happened multiple times, well, I want to go back to Egypt or India or wherever, and I'll only be a week. And I'll tell them, no, you're not. I said, if you got to go to India or Egypt, at the minimum you stay is 3 weeks. When people, say, well, I want to take a week off to go with my family. Say, no, a week is not enough. Take 2 or 3 weeks. And I'm still, my students are incredibly productive, not because of that. Your brain gets tired like anything else. And if you're working at 100% of the time, you can only do it at 80% capacity. So you are working all the time, but you're not really firing on all cylinders and you're cranky and you're tired. Do it my way, do it the European way, and that is you're working 80% of the time at 100% output, and you're having a hell of a time. So the idea with the boat and the sailing is I have a lot of other passions outside work that I'm equally passionate about. And so when I take time off, I'm either skiing or sailing a cat. This is not a regular sailboat as you see.
Mm-hmm.
And I do that all summer. So I have a house near the shore. I go down there beginning of the summer and I stay there for the most part. I only come back 1 day a week to meet with my students and then go back. And then essentially when the weather is good and it's windy, then I drive to the beach and go sailing. And I come back at the end of the summer extremely refreshed.
I will again ask about this your spare time in Beyond the Lab. Anyway, before that, I would like to ask a question about one of your amazing books, Fundamental uh, Ce- um, Fundamentals of Ceramics, which is the book I know you from that book. This was a textbook for several of my the courses I took during my master's, and it's a great.
Where did you get your master's in Iran?
Yes, yeah, Shiraz University in Iran.
Shiraz. Okay, yeah.
Uh, and I think I found it. I found this book an interesting and amazing textbook for graduate students.
And
2009, I think the first edition. Am I right? It should be around 2008, 2009, I think, or maybe uh, 2000.
no.
Uh,
So the history, so when I came to Drexel, they didn't have anybody who knew ceramics. So every year, we have a quarter system. So one quarter I would teach undergraduate ceramics, and another quarter the same year, I would teach graduate ceramics. So the first thing I did when I started in '85 is I assigned a book that I use, Kingery, Bowen, and Ullman from MIT, which wrote Introduction to Ceramics. It was a big, thick book, and 3 weeks into the semester or the quarter, I realized it's not a textbook. It's a good reference book if you are, if you know what you're, and you just want a
mhm,
refresher, then that's an excellent book. But it's not a good. It doesn't really teach you anything. It just puts down these equations, doesn't explain where they come from, etc. So I decided. So I scrambled and I made a package of different papers and different subjects and ceramics, and I put them together and I gave it to the students. Of course, it was not very good because you have all these different symbols and everybody's doing their own thing. So that's when I decided to write my book, textbook. And that took me 11 years. And the first 10 years, essentially at Drexel, I didn't do much research and I was laser focused on writing this book.
mm,
And I think the first printing, I think, came out in, I want to say 1997, maybe.
mm. So I got the second
Anyway, that was
edition.
that was McGraw-Hill, and then in 2000, I forget what. Anyway, in 2000, I don't have it here. Let's say early 2000s, McGraw-Hill decided they didn't want to print it anymore. So I went to Institute of Physics, and that was great because that first edition, that first printing had so many typos, despite the fact that I worked on it for 10 years.
Mm,
It still had so many typos. So what happened between the first printing and change, what happened when I changed publishers is I fixed it. Right, fixed many of them. They're still, you can never get rid of all. It's Murphy. It's never going to happen. You're never going to get rid of all your typos. Anyway, so that went on for a while, and in the 2000s, and it was the book. You probably used that edition,
yeah.
Institute of Physics, and then in 2020, I up I upgraded the book. I came up with a second edition,
Mhm.
and that was published by Taylor and Francis. And that's I don't know when you were taking classes,
I think it was
but
around 2008 and the version that I
yeah,
got.
yeah. So you must have did you have the orange one?
Yes, yeah, the orange one.
Yeah, that's the IOP.
Yeah, IOP.
Yes, and that's the one that worked for a long, long time. And now I have a second edition with, like I said, Taylor and Francis. Yeah, and that one is really a beauty. There are two colors, and yeah, I spend a lot of time making the figures, and I expanded some of the sections. So the second edition I strongly recommend you get a
Of course,
copy.
yeah. I'll
It's
get it.
very, very nice. Yeah.
Uh,
But again, this was one of those things where, you know, I'd wake up and I didn't want to do anything except write the book.
mm,
I mean, that was a passion. I mean, that was like I said, a work of love. I mean, I love that book,
mm,
and I think if you take everything away from me and you just leave the book, I'd be happy
mm.
with that being my legacy.
Amazing. Yeah, that's a lovely book. I love the
Thank you.
book. Um, so I would like to I would like you to compare the being a graduate student now and the time at the time you did your graduate studies as a PhD student, I mean, how has it changed?
No,
And
yeah, it's fundamentally different for many reasons. It is, um, first of all, that pressure that people have to graduate was not there necessarily.
Mm,
It took me a long, I mean, when I was in high school and I would listen to friends of family and everybody else, and everybody would say, "Oh, the best years of my life were when I was in college." So I took that to heart and I applied it to my life. So when I graduated from MIT with a PhD in 1985,
mhm,
I had 14 years of college because I was having a grand old time. And, the time allowed you to do that. The pressure to graduate and publish papers, everything else, it was just not there. I mean, and that sort of translated into other things. For example, yeah, I had a good PhD, but I didn't have that many publications, and yet I could get a faculty position in a big city on the East Coast, which was my dream anyway. Today, you're competing with the entire world.
mm,
Everything is no longer local; it's global, which makes it, of course, a lot more difficult because the competition is getting better, and more importantly, there's a lot more of them. So I don't envy you guys. I don't know in what stage of your career you're at, but yeah, it's harder now,
yeah.
and no doubt about it. It's also harder to, I think, get funding if you're starting out. So yeah, it's just harder. Let's just put it this way. I mean, it's still fun. It's still your graduate years have to be fun. If they're not, if you, I tell my students, and that's also something that's very important when they come and meet me for the first time, and I mean that sincerely. I say, look, if you're not having fun in graduate school, you never have fun.
Mm, yeah.
And I make sure that they have fun. Now, of course, this is not very common because most faculty, they think that if they push their students like slave drivers, they'll get more. And no, they don't. All they get are disgruntled graduate students that can't wait to leave. By the same token, when you work with me, and like I said earlier, Tamer graduated in 2.5 years. I just had a guy, Adam, he graduated in less than 3 years.
Amazing. That's great. I mean, uh, yeah, in chemistry department in the University of Manitoba, where I graduated, the culture is, I think, 5, 6 years. That's the
Mhm, mhm,
culture. I don't
mhm.
know why.
Was it chemistry?
Yes, yeah. I did
Yeah,
in my
chemistry and physics are different, right? Materials is, yeah, well, the materials I think I have to look it up on AI. You can do so, what's the average number of years a typical graduate student spends in getting PhD in materials? And my guess would be about 5 years,
mm,
with some, of course, going to 6 and some finishing in 4. But the average, I think, is probably 5.
mm.
And
Okay.
I think if you look at my students, my group, it's probably closer to 4.
Mm, great. So, for the last question in this part, I would like to ask you, uh, what are the common mistakes uh, young material scientists repeatedly make. I mean, but by young material scientists, I mean those who are graduate students, postdoc, early career. I mean, those who have started their faculty position recently. Uh, what do you think? What are the most common errors?
The first thing you have to do is do your homework, right? So you get accepted at a university, right?
Yeah.
Let's pick Northwestern just for the fun of it, because my son went there. And so the first year, you're taking classes, and then you decide on an advisor. Okay. And the first um, advice is find something that you find very interested or you really care about. That's number one.
Yeah.
Okay, so you find somebody who works on solar cells and you think solar cells are the best thing ever. Great, good. But there's a huge but. Before you ever commit, talk to that person's graduate students and postdocs. Ask them, take them out to lunch, buy them lunch, and sit there and ask them about the atmosphere. You know, what's the general, are people happy? Are students happy? Are they not happy? And that's even more important that what you want to do. So that's the first thing. First mistake people do. The second mistake that a lot of people, okay, well, yeah, a lot of people do is they try to answer questions that many times are not totally completely, but they're not going to have an impact in the following sense. So that when we do research,
Mhm.
um, when we do research, you can do two kinds of research. Well, they're related, but one of them can be purely science. Okay, if you want to do that, great. Then your chances are you're going to end up in academia, and then your main responsibility. My main job is to educate the next generation of material scientists. Okay, that's my main job. I use research to do so, but I consider that to be my number one priority. Okay, I have to bring young people in, train them to be critical, send them out. So, however, and this so you can work on science, and then there are no bad questions to answer.
Mhm.
However, if you want to make a difference, if you want to have an impact on the world, then you need to work on practical problems. You're still doing science, you're still doing almost basic science, but but if it works, okay, could this be the next generation materials? Now, I've been very, very lucky because I had the MXene, and the latest one, this one-dimensional titania that is unreal. This latest discovery in 2022. They all will lead, hopefully, to something commercialized. So my trifecta, the paper, every work I do, I'd like it to be published in Nature Science, be patented, and be licensed.
Mhm.
In many cases, what you're working on will never really translate for many reasons. So I'll give you one example. All right, so I don't know if you know oxygen evolution reaction. Do you know what that is?
No.
OER. Oh, it's a catalytic reaction for splitting water. Okay,
Yeah.
great. So now you're young faculty, and you go, I did my PhD on ER, I want to work on OER, and then you submit a proposal to NSF or whatever, and you, for example, propose to see the effect of rhodium or the effect of platinum or the effect of gold on OER. That's great science, good for you, but it's not going to go anywhere, because
Mm.
people have known that platinum works beautifully, and the problem is not the platinum. The problem is the cost of platinum. Another example that's very, very in the lithium ion business, I'll give you another example. So you're a graduate student, and I'm faculty, and I decided to write a paper. That's how we discovered MXenes, on the hydrogen evolution reaction. Okay, the hydrogen evolution reaction is the one when you split water, you have oxygen on one side, hydrogen on the other. Okay, great. But very quickly in your reading, you realize that HER is not the rate limiting step, it's OER. So if you want to make progress in the field, don't work on HER, work on OER. Sorry, on the oxygen evolution reaction. Now it turns out the OER is a much, much, much more difficult problem.
Mm.
So you have to balance, okay? You have to balance. But like I said, if you come up with a cathode that doubles what we have now as a cathode, it's revolutionary. If you double, I mean, and the numbers on the anode side are just off the charts. I mean, they're just huge. You don't need that, or at least you only need that if you can get the auction evolution to come up to the HCR. I don't know if that makes sense.
Yeah, yeah, yeah. Thanks. Yeah, I think these are the important things. You mean that it's not just only about science. We need to think how is it possible to work more on one subject? How easy it is? Are materials available? Is it hard to develop something new? Is it hard to characterize? There are so many things going on. It's not just about science. I get it. Thanks.
Yeah, I mean, but I think, yeah. So the other, another example I love to give. So, you heard of supercapacitors?
Yeah, yeah.
Okay. All right. So I worked on supercapacitors for many years because MXenes are fantastic supercapacitor material. All right.
Yeah.
And I was doing this work. I was doing what everybody else is doing, putting capacitors together and publishing papers. All was good. And then one day, and one day I asked my students, well, we need to know what the self-discharge rate is. Okay. So what does that mean? You make a cell, you charge it, right? And then you measure the voltage as a function of time.
Mhm.
Okay? If you do that with a lithium ion battery, that voltage is not going to change for months, right? I mean, you can travel 6 months, come back, turn your car on, and it will turn on, right? Now, it turns out that the self-discharge in supercapacitors is of the order of 24 hours on a good day, where you lose half your charge. And yet people are trying to sell you the idea that these supercapacitors are going to replace batteries in cars. Well, I have bad news for them. That's not going to happen.
Mm.
And then so what you notice then, something again fascinating is, I don't know if you have how much electrochemistry you have, but once you set up the cell, Mushtaba, the easiest experiment you can do in the history of science is measure the voltage as a function of time
Yeah,
and report it.
exactly.
Nobody does. Fascinating. Nobody does. We're the only people, publishing these papers saying, "Oh, we also measured the rate, the discharge rate, and it's not very good." But and it's again. I mean, I have a lot of these examples, and so I don't want to get into the politics of science. But here's a piece of very good advice for anybody starting out.
Mhm.
Really good advice. If you get into a new field and you realize that there's this very simple experiment that nobody's doing, okay? That's a very, very big red flag. So supercapacitors is a great example, okay? Everybody's publishing about how large capacity and how fast you can charge them, but nobody's publishing self-discharge. Again, the simplest, I mean, that experiment just right, you already set up the cell. All you have to do is leave the voltmeter on, or you don't even have to leave the voltmeter on. You can decouple the voltmeter, go home, come back after 24 hours and measure the voltage.
Yeah.
Okay. So yeah, so that is, I sort of made somewhat of a career doing that. Is essentially going in and saying, guys, what you're doing is not, it doesn't hold water. And
Mm.
that, yeah.
Yeah, interesting. Good points. Thanks. Thank you for sharing. Let's move to beyond the lab. I would like to ask a few questions about the personal aspects of your life, if you don't mind. Already, I think you answered one of them. What do you do in your spare time?
Like I said, I have multiple passions. I play squash twice a week. So that's one of my passions. I've been playing squash now for 50 years or so.
Mhm.
And I still play twice a week, Mondays and Thursday. I ski, but I don't ski very much because I ski 4 days a year. So, but I love every minute of it. I sail. That's very big for like I told you, in summer I sail.
Yeah.
Um, I like to read. Essentially, what I tell my students, I like to travel, but what I tell my students and is that you have to cultivate a few passions outside of work, so that when you take those 20% days off, you're not bored.
Yeah, that's true.
You know what I'm saying?
Yeah.
And that can be anything. I mean, what again, that 20%, again, if you work on the European system, that 20% is something you can cultivate. And even if your job is not your passion, which 95% of people hate the job. Hate is a strong word, but 50% definitely hate the job. And another ones don't really, are not that great keen on it. Then find something to do in those, what I call recharging time to do something that you're passionate about. And again, it can be, playing music, cooking, making bread.
When you were a kid, what was your dream job?
You'll find that amazing. But when I was 10 years old, I knew two things. One, I was going to come to America. Two, I was going to be a faculty member.
Amazing. So you knew what you want to do.
Yes, it was. And when people ask me why, how, I don't really know.
Hmm.
But no, well, I did know very early on, I don't know, maybe when I was 10, is I was not going to stay in Egypt for many reasons. One of them is that, yeah, the main one is back in 77 when I left Egypt, okay? There were 40 million Egyptians, okay? That was the population of Egypt. And at the time, in 1977, I thought 40 million Egyptians was too much. Today, there's over 110 million Egyptians. And you know Egypt, right? They're living on very thin, this very thin, uh, 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 um, around the Nile,
Mm,
right? So it's not much land. It's not like Iran or it's not like India or China where there's a lot more area.
mm,
So you know that a country like that is not going to go very far because whatever I mean, you need to, okay,
yeah.
Egyptians increased by one point something, maybe 1.2, maybe even 1.5 million a year. What that means, if you want to employ them all, that you have to generate 1 million jobs a year.
Yeah.
Well, that's not happening.
In another world, in a
In
parallel
other
world,
words, yeah, another time, if I had to do it again,
yeah,
yeah,
which job you pick?
yeah, no, I would. I'm one of the very lucky people. I got my passion was my job. So yeah, if I had to go back and do it again, it would be exactly the same.
Okay. You don't want to try anything else?
Nope,
Okay. Uh,
nope, no interest whatsoever.
yeah. So, any regret in your professional life or in your life you would like to share?
Mm, no, no. I mean,
Uh,
made mistakes like everybody else, but
yeah.
nothing really that I really, really regret. No.
If a time machine existed, would you rather go 100 years forward or back?
That's a good question. Yeah, that's a very good question. I
Maybe you
guess,
maybe you want to go, I don't know, thousands of years back to see the
yeah,
pyramids.
well, if I can go back, I wrote a paper on the pyramids of Giza, right? And that some of the blocks are cast rather than carved, which is a long, long story. I can send you the link. I have my whole presentation there. So yeah, if I could go back 4,500 years to
Mhm.
figure out how the ancient Egyptians, not building the pyramids, that is not even close to what I'm going to tell you. They carved granite like it was butter. It's insane. And I don't even have a working hypothesis, right, as to how they did that, which for a scientist is bad. Okay. I mean, you should see some of the carved stuff, right? And it's like you go in the king's chamber in the Great Pyramid, right? And it's all encased in 70-ton beams of granite. Okay. You run your hand on that wall, you barely feel the seams. So smooth and so perfectly 90 degrees. Everything is so incredibly perfect that the only way you could do it today maybe would be with lasers. Maybe high power lasers. How they did that without even iron, yeah. So that definitely I would want to go back
Yeah.
4,500 years to find
So,
that out.
the aliens theory, do you think it's
Well,
just
that's what that's what I'm going. I mean, if it was aliens, I ought to meet them.
yeah. That's gonna be an interesting things. Uh, yeah, that's very strange. I've
No, but you have to look at, so go look at some of the pictures. Just go on the internet and type granite carving, Old Kingdom.
mm,
And in Saqqara, there's a tomb. In that tomb, they have a sarcophagus that people measured, the whatever dimensions.
mhm,
And it's just insane.
mhm,
The exact, it's not, there's the root mean square of the surfaces and the angles, they're all perfect.
mhm,
And I don't know how they did that just with stones, but anyway, yeah, so that's where I definitely would want to go.
interesting.
Now, 100 years, yeah, I mean, I think 100 years, I probably would want to be, I'll go forward to see how bad we mess up.
Yeah, I don't know how it looks like 100 years. It's scary, you know.
It is very, very scary. I mean, I don't say that very often, but I'm glad I'm 71.
For the last question, who is your favorite scientist in the history?
Oh, no doubt. Richard Feynman.
Chet Feynman.
You ever hear of Richard Feynman?
I've heard his name, but
Yeah.
he's a
Yeah, but
physicist, right?
yes. He got a Nobel Prize in quantum electrodynamics, but he was a fabulous character.
Thank you, Professor. Thank you so much for your
You're
time.
welcome.
Have a good day.
Yeah, thanks. Bye.